In general, it should not be necessary for designers to instantiate a buff-h primitive in their design. The implementation tools will use the buff-h primitive appropriately when routing your global clocks. The role of the buff-h primitive is to drive a horizontal global clock row into each clock region. It is effectively an extension of the global routing resources. Each clock region, again, has 12 buff-h's, or 12 buff-g's. The buff-h can distribute a clock at up to 800 megahertz. There is also a buff-h clock enable primitive with a clock enable input. This is helpful for turning off a local clock into region to help minimize power consumption of your component. When using the buff-h or the buff-h clock enable with the ISE 11.3 software, an area constraint may be required to keep all the clock loads within a single clock region. Regional clock buffers serve vertically adjacent clock regions, so they act as additional routing resources for clock signals that do not need to route to so many clock regions like a global, or at least not immediately neighboring clock regions. Now, the regional clock networks reach the clock inputs of all the synchronous elements within the region. There are up to 8 buffers per clock region, and that means 4 per I/O bank. And again, these can be driven by your clock-capable I/O pins, general interconnect, the output of the GTX transceivers, or your local MMCM's high-performance clock outputs. These can drive logic, I/O logic, other MMCMs, as well as the global routing resources or buff-G. For medium and high-performance clocks, driving 1 to 3 regions is really ideal and what these are intended for. So these are not your global routing resources. There's also the functionality for the buffer frequency to be divided, anywhere from 1 to 8. Now, the clear and the clock enable inputs allow the user to control the reset condition of the clock divider in the buffer, as you'll note from the figure. This allows the user logic to know which rising edge of the incoming clock corresponds to the rising edge of the divided clock. The I/O clock buffers are designed to route clocks within the I/O columns. There are 2 single-region buff I/Os and 2 multi-region buff I/Os in each I/O bank. These can be driven by the clock-capable inputs in the same I/O bank, the MMC outputs via your high-performance paths, which are dedicated to silicon and designed to route these signals very quickly. They can drive the I/O logic in the same and adjacent I/O banks. The buff I/O can drive logic resources only in the same I/O column. And again, these are intended for clocking high-speed I/O logic. Now, the 4 clock-capable I/O pairs in each I/O bank are identified by the letters CC in the pin name. The pins that correspond to the buff I/Os that can drive multiple regions are designated by the letters MRCC, or multi-region CC. Single-region pins are designated SRCC, or single-region clock-capable. The I/O clock networks can drive the clock pins of the IOB resources only, that is, the DDR and SDR flip-flops that are associated with the I logic and O logic block, which is of course associated with each I/O pin. The I SERDES and O SERDES resources as well. Because of the low fan-out nature, they have extremely low skew and very short insertion delay, which makes them ideal for source-synchronous interface applications. Now, source-synchronous interfaces can be easily built with Virtex-6. So in this example right here, we see our data coming into the iSerdes resources and a clock-capable signal, or a clock, coming to the CCIO pin, which is then routed via the buff I/O to the iSerdes resources, as well as through the buffer resources to our FPGA fabric, which is then taking the data from the iSerdes resources. The I/O and the regional clock networks combined with the iSerdes and the OSerdes provide powerful tools for creating source-synchronous interfaces. The buffer will be set to divide by n if the interface is single data rate, or divide by n over 2 if it's a double data rate application. Now, the n can be 2 to 8 in SDR and anywhere from 2 to 10 in a double data rate application. The buff I/O and buffer in a region are going to have the same driver, that is, the clock-capable I/O signal. They are intended to be used together to create the 2 clocks, that is, the high-speed and a low-speed clock, required for the SERDES. This explains why the buffer resource does the clock division. The output of the buff I/O and the buffer are guaranteed to be in phase, allowing proper clock crossing between the clock and the clock div in the iSerdes and OSerdes resources. Please note that all of this, that is, the clock buffer, the networks, the regional driver, the iSerdes, are all in one clock region in one column. This is how extremely high speeds can be achieved with the I/O resources in Virtex-6. The performance path routing enables fast I/O interfaces. This has been optimized in the silicon and is handled automatically by the implementation tools. There are 4 performance paths driving each inner-outer, that is left and right I/O column from your local MMCM. And these are driven by the MMCM outputs, specifically outputs 0 through output 3. So the other outputs cannot drive these performance path routing. Now these can drive the buff I/O resources in the I/O column, the buffer or the regional clock resources, as well as the GTX serial gigabit transceivers. These are powered by a regulated supply within each MMCM. This isolates the clocks from noise on the VCC internal power supply. This provides the cleanest path from the MMCM to the I/O columns and offers low jitter than any other routing resources available in Virtex-6. Now, as I mentioned, software automatically will place the critical signals onto the performance path routing when you build your design or instantiate the appropriate resources. Now, please note, again, if you connect the outputs of the MMCM to the buff I/O, buffer, or GTX, this must be connected with the outputs 0 through output 3 of your MMCM, which will use the advanced performance path routing. But if you don't, then your output performance on this performance path routing will not be used and your performance will degrade. So again, be sure and use output 0 through output 3. So this slide is trying to summarize the I/O and the regional clocking resources that we have associated with Virtex-6. So first of all, your clock-capable I/O pins exist in all I/O columns. There are 4 clock-capable I/O pins per I/O bank. 4 are differential using 8 pins, and 4 are single-ended, which would use 4 pins, of course. And these are adjacent to the H-clock rows. So there's 2 clock-capable I/O that can drive above, and 2 clock-capable that can drive the logic below your H-clock row. The performance is about 800 megahertz, particularly in differential applications. The I/O clocks exist in all I/O columns. There are 4 buff I/Os per I/O bank, up to 8 I/O clock networks per I/O bank. And some clocks are local only. Some can drive the neighboring banks as well. And again, these support speed up to 800 megahertz. The regional clocks exist in all I/O columns. There are 4 buffers per I/O bank, 6 regional clock networks per region, and these span up to 3 regions, meaning 1 above and 1 below, as well as this original source region. And they support a clock divider range from 1 to 8 and operate at up to 500 megahertz. This slide is summarizing the global clock routing resources. So for global clock inputs to the iBuffG or the iBuffGDS, there are 8 total. 8 differential using 16 pins or 8 single-ended using 8 pins. And their performance is up to 800 megahertz differential for maximum performance. They support high fan-out and giving access to all clock loads in the FPGA and are designed for low skew and a short clock insertion delay. If you're working with the global clock multiplexers or the BuffG control primitive, there are going to be up to 32 global routing resources, and these drive the global clock networks, and they support an optional clock enable, and they offer a guaranteed glitchless clock switching function. Now this slide is designed to summarize the clock network functionality. First of all, each region supports now a 40 CLB height, so the density of each clock region has increased from Virtex-5 from 20 to 40. The clock regions now match all the I/O banks. There are 4 differential or single-ended clock-capable inputs per I/O bank. There are 4 regional buffers per I/O bank as well, and remember, some of those, depending upon the placement of the clock region, will drive neighboring clock regions as well. The clock regions will span 1/2 the die, just like in Virtex-5. There are 40 or 80 I/Os per clock region as well now. And one of the things to note, of course, is when you want to look in pin ahead and determine which of the I/O banks you're driving to will show you how many I/O pins you have per clock region that you may be choosing. There are 4 buff I/Os per I/O bank as well, and it supports 12 global clocks to be routed into each of the regions. Now, depending on the specific device, a clock region can have 1 or 2 I/O columns. This will affect the number of I/O pins and the buff I/Os and buff Rs per clock region. It does not affect the number of globals or regional clock networks that are supported per clock region.